Assalamu alaikum warahmatullah. Hello and welcome back. This is your brother Wasil with a new lesson today. We'll be discussing about polysaccharides, their types, and few examples from each type. Inshallah. So polysaccharides, they can be simply called as glycans. They consist of repeat units of monosaccharide units which are linked together through glycosidic linkage. The polysaccharides, they serve basically two types of functions, that is structural function and storage function. Polysaccharides are linked. This is due to the fact that the carbonyl carbon can attach to any of the hydroxyl carbon, which is in contrast to the if we see proteins and if you see the structure of nucleic acids, they are always linear. But polysaccharides are branched, and this branched structure is due to the occurrence of hydroxyl groups, and they can attach, they can form bonding with any of the hydroxyl group. That's why they are branched. Okay, so depending upon the types of the monosaccharide units, that is a mixture of monosaccharide units or single monosaccharide, we call these polysaccharides as homopolysaccharides and heteropolysaccharides. Homopolysaccharides are those polysaccharides which yield only single type of monosaccharide on hydrolysis, and heteropolysaccharides are those polysaccharides which yield different types of monosaccharide units or mixture of monosaccharide units or their derivatives. Okay, uh, if we study now homopolysaccharides, what are homopolysaccharides? As I told you, homopolysaccharides are those polysaccharides which yield only single type of monosaccharide unit on hydrolysis. For example, we have starch, we have dextrins, we have inulin, we have cellulose, we have chitin. Okay, we'll be studying about starch and glycogen. So, starting with the starch, starch is the carbohydrate reserve of plants and is the most important dietary source of energy for higher animals, including man. Starch is mostly found in the cereals. It is found in vegetables, in tubers, in roots, etc. And starch is a homopolymer which is composed of D-glucose units which are held together by glycosidic linkage. Since these homopolymers, the naming of these homopolymers depends upon the type of glucose, sorry, not glucose, depending upon the type of monosaccharide unit that they are made up of. And for example, if there is a polysaccharide which is made up of homopolysaccharide, which is made up of glucose, we will call it glucosan. That is, I told you in the starting of the lesson, I told you polysaccharides are known as glycans. So uh, if there is a homopolysaccharide which is made up of glucose units, we call it glucan. If it is made up of fructose units, we call it fructosan. So starch, since it is made up of glucose units only, exclusively glucose units which are held together by alpha glycosidic linkage, we call it glucosan or glucan. Okay, now starch, it consists of two polysaccharide components. One is known as amylose and another is known as amylopectin. Amylose is a water soluble component which is 15 to 20% of the total starch content, and amylopectin is water insoluble, which is nearly 80 to 85% of the total content of starch. This amylose amylose is a linear chain of 200 to 1000 glucose units which are held together by alpha 1,4 glycosidic linkage. I hope when I say alpha 1,4 glycosidic linkage, it will be clear to you what is alpha 1,4 glycosidic linkage. That is, anomeric carbon 1 is linked to the carbon number 4. That is alpha 1,4 glycosidic linkage. Why alpha? Because it will be alpha anomeric carbon. Okay, alpha anomer. So alpha 1,4 glycosidic linkage, this is amylose. We were talking about amylose. It is made up of only glucose units, 200 to 1000 glucose units held together by alpha 1,4 glycosidic linkage. Okay, and another is amylopectin. It is in contrast with the amylose. Amylopectin is branched at after every 20 to 30 glucose units. There is a branch. At the branch point, the glucose units are held together by alpha 1,6 glycosidic linkage. That is, carbon number 1 is in linkage with the carbon number 6. I will show you when I will make structure of amylose and amylopectin. I will show you there how is alpha 1,6 glycosidic linkage made. So alpha 1,6 glycosidic linkage at the branch points and rest anywhere on the chain. It is alpha 1,4 like amylose in amylopectin as well. Okay, so starches, they are hydrolyzed by amylase enzyme, and amylase is present in our saliva. It is present in our pancreatic juices as well. And this amylase enzyme, it is specific to alpha 1,4 glycosidic linkage only, and this amylase, it hydrolyzes the starch to dextrinase, that is the intermediate products of starch digestion, dextrinase, and then from dextrinase to various types of dextrinase, and then dextrinase to maltose, and finally to glucose. Now I will show you the structure of amylose and amylopectin. Now I will make the structure of starch, and it is polypeptide, consists of two components. One is amylose and another, as I told you, amylopectin. Now first we will form the structure of amylose. Since whether it is amylose or amylopectin, it is a homopolysaccharide starch, so it is formed of only D-glucose units. D-glucose units. So D-glucose units will be present in amylose as well as in amylopectin. There will be no difference. The difference will be in the bonding. And what difference is that, I will show you at the time when I will make the structure of amylopectin. Now first let me make the structure of amylose. Since amylose is made up of D-glucose units, so we will first make the structure of D-glucose. I will not show carbon units here now from now on, because it will be clear to you. Now this is the oxygen. Okay, so these points are the points where the carbons are present, where shown. यहाँ पर मैंने दिखाया था कार्बन को, ठीक है. तो since ये D glucose है, so it will be OH, again OH, H, again here H, OH. Since it is alpha D glucose units, alpha 1,4 glycosidic linkage means it is alpha D glucose. Okay, so it is OH here downside and H here, and it is like this, O here. Okay, H and CH2OH on its usual place. Now what happens when these glucose molecules, like in maltose, there were two glucose units that were held together by alpha 1,4 glycosidic linkage. Similarly, it is like this, it is like maltose. Okay, so we'll be again making the alpha 1,4 glycosidic linkage, another D glucose, this is another OH, this is H again, OH, OH here, H, CH2OH, this is H and OH. Now what happens, there is bonding between these two, carbon number 1 and carbon number 4. This is carbon 1, anomeric carbon, this is carbon number 4. Okay, so there is bonding, and the glycosidic linkage is between carbon 1 and carbon 4. So this is alpha 1,4 glycosidic linkage here. Now what happens, there is a chain of these molecules. Another molecule will come up, add up from here, another from here. So from both sides there will be these D-glucose molecules that will be adding up to the chain until they become 200 to 1000 glucose units. That forms the amylose. So we'll be showing like this. So we won't be showing OH here, we'll be showing like this, and we'll be showing here O. फिर हम इसको ऐसे brackets में रखेंगे, we'll keep in parenthesis, so as to show it that it is a continuous molecule. It's not just two molecule, but this is the repeating unit. This is the repeating unit in amylose. So this is amylose, or we call it simply alpha amylose. Okay, amylose unit. This chain repeats continuously unless they are 200 to 1000 molecules. Okay, so that is amylose. Now in amylopectin, since amylopectin is also made up of D-glucose units, what happens, this chain will be again similar. D-glucose units held together by alpha 1,4 glycosidic linkage. I'll be making them again. You see, this is the D-glucose. Azan ho rahi hai to rakenge. So now the azan is over. So we were making this alpha D glucose molecule again here. You it is again pattern will be same here. It will be OH here, H, H, OH, OH, H, H, and CH2OH here. Okay, so there will be another molecule of D-glucose here, like this. OH, H, H, OH, OH, H, H, CH2OH, H. Now, what happened at this? If you see, there will be again glycosidic linkage between the carbon 1 and 4 in amylopectin linear chain, in the linear chain. Okay, but as I told you, at the branch points, wherever there is a branch point, and that branch point existed after every 20 to 30, some say 24 to 30 glucose units. So after every 20 to 30 glucose units, there will be a branch point. Suppose this unit is the 30th glucose unit. So we will show it here like this. So branching will continue from this side. Branching will continue from this side up to 1. That is, there will be 30 glucose units, and this is the 30th. Suppose, for example, if we take, so what will happen at this point and the 30th point, there will be a glycosidic linkage, alpha 1 6 glycosidic linkage again with the glucose molecule. ग्लूकोज मॉलिक्यूल के साथ ये होगी, क्यों डी ग्लूकोज मॉलिक्यूल के साथ? क्योंकि जो स्टार्च है ये होमोपॉलीसैकेराइड है, इसमें एक ही टाइप के मॉलिक्यूल्स है, एक ही टाइप के दिस मोनोसैकेराइड यूनिट्स है, एंड दैट इज डी ग्लूकोज. So there will be D glucose here as well. So we'll be making a D glucose unit here. This is a D glucose. Okay. Again, this is H, OH. This is OH, H. This is H, OH. This will be OH, H. This will be H. और यहाँ पर जो है at this, it will be now CH2 and O. CH2 and O, because this anomeric carbon at this point, the carbon 1, this is the carbon 1 anomeric carbon of this molecule. So this anomeric carbon will bond with the carbon number 6, OH group of the carbon number 6, and this is the carbon number 6. So at this OH group, there will be bonding between the anomeric carbon and the hydroxyl of this group of the 6th carbon. So that is why we call this bonding as alpha 1,6. Alpha, we call it alpha 1,6. Why? Because there is a bond between carbon number 1, that is anomeric carbon, and carbon number 6 of another glucose molecule, and we call this bonding as alpha 1,4. Why? Because there is bonding between carbon number 1 and carbon number 4. So similarly, we call it alpha 1,6 because there is bonding between carbon number 1 and carbon number 6, and the rest here will be again a linear chain, again from this side as well. Oh, so this will continue again up to 30 glucose units, and it will be linearly bound, and the glycosidic linkage will be alpha 1,4. And at the 30th unit, there will be again alpha 1,6 glycosidic linkage like this. So this when this amylopectin molecule containing a few thousand glucose units, it looks like a branched tree. It looks like a branched tree. That is, after every glucose, after every 20 to 30 glucose units, there is a branch. So when you see thousands of these glucose units of in amylopectin, they look like a branched tree. Okay. So it was about starch, and now we'll be discussing about this glycogen. Glycogen is the carbohydrate reserve in animals. That is like starch in plants. In animals, it is glycogen, and hence glycogen is also known as animal starch. It is also known as animal starch. The concentrations of glycogen are very high in liver, followed by muscles and brain. Glycogen is also found in plants which do not possess chlorophyll, for example, in yeast and fungi. Glycogen is also a polymer of D-glucose units, which are held together by alpha 1,4 glycosidic linkage, as well as alpha 1,6 glycosidic linkage. That is like amylopectin. The structure of glycogen is similar to amylopectin, but with very frequent branching. In amylopectin, the branching would have been after every 20 to 30 glucose molecules. But in glycogen, we see branching patterns after every 5 to 6 glucose units. So there is very high branching in glycogen as compared to this amylopectin. But the structure of glycogen and amylopectin is same, so I don't need to make it again. It is same branching this structure, but branching pattern is different. There is branch at after every 5 to 6 glucose units in glycogen. The molecular weight and the this number of glucose units in glycogen vary as according to the source from which they are obtained. The mostly we write generally the molecular weight of the glycogen is up to 10 to the power 8, and the number of glucose units we write generally we write 25,000 glucose units in every glycogen polymer. Okay, so this was about glycogen. So there is again alpha 1 6 and 1 4 this glycosidic pattern. And which enzyme will break glycogen? It's again amylase. And because amylase, this enzyme, it is specific to alpha 1 4 glycosidic linkage. So alpha 1 4 glycosidic linkage will be broken by the amylase enzyme. As in starch, here in glycogen also it will be broken by the this amylase, alpha amylase enzyme, pancreatic amylase as well as salivary amylase. And for alpha 1 6 branching, there is another amylase enzyme which is specific to alpha 1 6 branch points, that cuts the alpha 1 6 branch points. And the alpha amylase, which is specific to alpha 1 4 alpha 1 4 glycosidic bonds, it cuts the glycosidic bonds, it cuts the chain at that point, so releasing glucose units. Okay, so this was about glycogen. So this was about the homopolysaccharides. I'll be back inshallah with a new video about the heteropolysaccharides. Till then, fi amanillah and take care.